you, right? Because that's why it's good that you ask questions. One of your friend actually very good. He actually tried the example 2.4. So he actually detected that the solution that I provided actually is from the textbooks. The matrix is constructed is based on the imperial units. So you can look at that. The attachment I put inside here is the whole question done in the imperial units. So the matrix is actually extracted from this solution here. So if you use the matrix unit, so your value in the matrix will be slightly different. Okay, so you can double check it. Right? You can double check with your friend and so on. So to get the matrix in the SI unit. Okay. So the matrix in the solution 2.4 that I provided is in the imperial units. So you can you can look at the questions. Okay. So the other one is one of your friend asking that if you can still remember that there is we talk about the curvilinear motions. Okay. When you differentiate the velocity and become with respect to time and become acceleration, so we'll get the acceleration function. So that acceleration function, you actually use these formulas to construct the function. Right? For example, maybe we can click in, so you can see that if I find the der over dt. So what you will get? You will get d theta over dt e theta. So this is formulas actually it will insert into the equation. Okay. So the other one like the de theta over dt. So what we will get? We'll get negative d theta over dt er. Okay. So that's why there is a negative come into the arrive in the equations. So you can base on this and relook at the equation if you are interested to look at how the acceleration function is being derived for the curvilinear motions. Okay. Okay, so then today I will start recording. Then we will look at our balancing topics. Okay, sorry. Okay, so we'll look at the balancing. So we actually stop here on the dynamic balancing. So just some recall that for static balancing, we only need to fulfill this summation force equal to 0 function. So again, the force here is referred to the centrifugal force. Right? Not the force caused by the gravity. So this is centrifugal force. So this force is actually the mass multiplied the normal acceleration. Okay? So so for dynamic balancing, so we also have to solve this. That's why we call it the static balancing is a subset of the dynamic balance. So for dynamic balance, we have to solve this force function. So at the same time, we also have to solve another one. We call it the moment function. So when we talk about moment function, then we need all this distance between the mass. So if you look at here, there is a distance. Okay. So when we solve the moment, then we have to choose any point. So as I mentioned last week, so you have to choose the reference smart in a smart way. And so normally we choose at one of the unknown. So for example, this MA, the centrifugal force here, right, is unknown. So we choose here. So when we solve the moment equations, so this one will not appear in our equation. So then we can straight away solve for the MB, RB. Yeah? So that's why if you look at here, it choose the point O. So that's why the A component here, the mass, the force from the mass A, it will not appear in the equation. So again, this is a vector. So we can always break it into X and Y component. Okay. So again, the omega, because all the mass is rotating at the same omega, so omega will always be removed from this equation, the top equation here. So whatever you see, the omega is always being removed. Okay. So now we look at the example. So we still refer back. We refer back to this diagram. So we have the mass M1, M2, M3. So for dynamic balancing, so we need two mass. Normally, or almost all the time, we need at least two mass, MA and MB, to balance it. So, but not necessarily MA and MB will be at the extreme end. So it can be anywhere in the center. Okay? So this balance mass is always affected by the geometry or the system of in your design, okay, whether where it can be put. So I give an example of the car tires, car wheel. So normally the balance mass that you can put in is at the rim, okay, at its rim. So that's why you will see a lot of metal wick actually is stick onto the rim. Right? You don't stick close to the axle because then the mr omega square will give very small impact, right? Because the r is very small. So normally they will stick the mass at the most outer possible radius so that you can reduce the mass added to the system to get the same amount of mr omega square. So that is what in the reality. Okay? So now if we look at here, it gives M1 is 1.2 kg, M2 is 1.8 kg, and then M3 is 2.4 kg. And then it gives us the location of this unbalanced mass. Okay? This is unbalanced mass. So the location for R1 is 1.325 meters at the angle. This one's supposed to be like that. At the angle of 113.4 degree. So R2 will be at the 48.8 degree with a distance of 0.822 meters. And then R3 is 1.04 meter at the angle of 251.4 degree. Okay? So that's why when we set that, when we say the angle, that's why there is a X and Y here. So that is the angle that we measure. Okay? So that's why they have the angle for M1, M2, and M3. Yeah. Okay, so there is the angle. So then for distance, so it will refer to another view. Okay. So this is I would say this is the side view. So then this will be we call it the front view. Right. So then we will find this. Okay, front view. Okay. So there is a L. So we have L1, L2, L3, and the location of the LB. So because the questions already set the O is a reference. That's why the measurement is all from the plane A. Okay, plane A. Yeah. So what we need to do is normally we need to find the mass radius products. Means the M, for example, MBRB. And the MA. Yeah? So and their angular location. Okay? So what is the angle? right? So what is the angle? Similar to here. So what is the angle? So that we can do this dynamic balancing and putting the right amount and angle of the balance mass at the plane A and plane B. Yeah? So it will be very similar to how we solve the dynamic force analysis. So because we have a vectors equation, so we can always break it into x and y component. So that's why your R1, R2, R3 will break to the x and y component. Okay. So you just calculated it, so you get the x and y, and based on the I don't explain again. So this is basically the R1 cos omega t, then R1 sin omega t. Yeah. So it's the same thing. So that's why I keep asking you to try. Right? When you try, then you will know where you don't understand. Because if you just read the slide I give you, so then when you really want to do on your own, you will be you will face a lot of problems, right? Because then you suddenly you do not know how to include all these angles and so on. So you must try yourself to redo. At least you just redo this. Okay. So there is R1, R2, and R3. So we have the formulas. So normally, if you look at that, we will solve the moment equation first. Okay? Because with the moment equation, for example, this case, because we set the reference, reference is at the A, so we can solve the MB, RB using this moment equation. Okay? Because when we set the plane A is at the reference, so the MARA is disappear from the equation, then we can find MBRB. Right? So we solve it the x and y components separately. Right? So in this case, we have the MBRBX, so we just substitute the value. Okay? M1 R1X L1. So remember this moment. M2 R2X L2, M3 R3X L3 divided by the LB. Any Noah? Any question? Okay, so this is how we get the MBRBX. So we just substitute the mass, radius, and the distance for each of the component. Right? So this is to solve the x component. So we'll get the 0.230. So the unit, because it's MRB, so it's kilogram meter actually, if you want to write the unit, because we are using the kilogram and the meters to solve. So it will be kg meters. So same thing we can do for the y component. So again, we substitute the same value, not same value. We substitute the M1 R1Y L1, and then M2 R2Y L2, M3 R3Y L3, and also the LB here. Okay, so we will get this MBRBX is 0.874 kilogram meter. Okay. So once we get the MBX and this is Y, MBY, okay. So we can find the actual MBRB. Okay, so just take the MBRB will be square root of MBRBX square plus MBRBY square. Okay, so we can find this. So MBRB is 0.904 kilogram meters. So then we have to find the angle. So we will take the theta B is inverse tangent of. So normally we will take MBRBY, y divided by the RBX. Okay. So we'll take this. So now you can check. So we get positive value here, positive value here. So what it means here is if we draw this, so basically it will be somewhere in the first sector. Okay. So the angle you find, the theta B, is basically that. So once you press the calculator, you will get this value. So this is the correct value. Then you don't have to do any correction. Okay. So you can always check with your, where is your MBRBY, where is your MBRBX. So if it's first sector, then the value that you calculated is correct. Okay. So, but in the case that if your MBRBY is positive, MBRBX is negative, then you'll find that it will be at this sector. So whatever you calculate is over here. Then you have to take 180 degrees minus the value that you calculated using your calculators. So that's why I highly encourage when we solve this, we sketch out this. Okay? So you will know where is your location, your angle. So now we already get the theta B and MBRB. So normally we will not solve this further. We just take it as a mesh radius product unless the question give the mesh or give the location to you, right? The RB. Right? For example, I mentioned the car wheel, the car tires. So the rim size, for example, is 16 inch. So your RB will be 8 inch. Okay? So then you can know how much mesh to be added at the rim for the 16 inch rim. Okay? So once we get the MBRB and its angle, so we can go on to put everything into the force equations. Okay. So again, force equation, we have been breaking it down to the X and Y component. So we just substitute all the value, including this MBX, MBRBX, and MBRBY. So we substitute it in with all the rest of M1 to M3 value there. So we will get the MARAX is 0.134, MARAY is negative 0.870. So now, again, this thing will be the same. So if we solve this, which is MARA, is the square root of MARAX square plus MARAY square. Okay. So when we come to here, then theta A is again the inverse tangent of MARAY divided by MARAX. So now you calculated. So you will get a value of negative 81.25. So what we can do is, so I take down this. Okay, so now if we sketch it out, so this is X, this is Y. So my MARAY is negative, so it's somewhere at the bottom here, and then my X is positive, so I will be in the fourth sector, right? So you draw this out. That's why whatever angle you calculated, because it's Y over X, so it will be here. So you get negative 81.25. So basically this one can be your angle because you measure clockwise, so you put the negative. Okay? Or else, if you want to take the angle from here, so I can say my theta A is 360 minus 81.25. Okay? So that is my angle. Okay? So That's why you sketch this, then you'll know what you calculated, whether that is the actual angle that you want to present it, right? So this is how we solve. So again, we will left most of the time we'll just left it with the mass radius products, right? So yeah, I think this is additional slides. Oh, this one is given that example here is given that when the RA is given, okay, as I mentioned, because normally we will just stop here, right, with the mass radius products. So if in the case that now this is mass radius products and the RA is given, so then we can find the mass. Okay. So this is for A. So you can just divide the mass radius product with the radius provided 0.75. Then we will know that the actual mass that you have to put is 1.173 kg. It's a mass radius products. So this is another scenario. For example, now you only have the mass of 1 kg. So where you have to put your this 1 kg mass in order to make the system balance, right? So again, you take the MBRB divided by the MB. So you'll know that the location where you have to put this 1 kg of MB is at 0.904 meter. So the angle will not change. The angle is still 75.27, which is what we calculated from the formulas we have. Right. So this is actually what happened in the real life also if we are doing the balancing. So maybe give you an example is like if you know what is cooling tower, okay? So if you look at the Utah buildings on the top there is a squarish tank, okay? Rectangular tank, okay? Something like a tank, but it's actually a cooling tower. So the fans also have to do the balancing, okay? Because the fans is huge and quite heavy. Okay? If you don't do the balancing, so at the end of the day, then the cooling tower will be shaking, and then it will cause your building in vibration. Right? So that is where we do the balancing. Okay, so that is what we do in theoretical calculation when we have all the data for the unbalance. So then we can easily find the amount of balance weight that it needs to put into the system. Right? So for again, just recap. So for static balancing, so normally we only need one balance mass. That's why we only need the force equation. But for dynamic balancing, so because there is a moment issue, so normally we will need two balance mass, right, at the two different plane to solve the problems, right? So now we look at how we can do measuring and correcting the imbalance. So there is a need to measure and correct the imbalance in the rotating system, right? So how well you want to correct it is always depend on the application and also the requirement from the system. So the best example assembly is the automobile tires and wheels. So because you may have the chance to look at it. So ideally manufacturers to be perfectly the product manufacturers is to be perfectly uniform in geometry and homogeneous in material. So that's why I say ideally. Okay? But in reality, especially this one is not 100%. You may achieve maybe 95 or 98%. Right? So the small percentage of non-homogeneous in the material will actually cause the weight distribution on the material is slightly different. That's why we still, whatever, how good is your manufacturing. So at the end of the day, we still have to check whether the system is balanced or not, especially for those very high rotating speed products. This is like turbine blades and so on. Right? So the rims is more likely to balance than the tires. Right? So the meaning here is the rim, after when they manufacture, the rim is easiest to manufacture close to a perfect balance condition, close to not actual, right? Because there is a metal casting parts most of the time, right? But tires, tires is actually much more difficult to control, especially on the homogeneous in the material, right? So if you ever watch or understand how the tire is being built, tire is built with a multiple layer of materials that including rubbers, steel wires, and then fabrics, threads, and so on. So it's not just pure rubber, right? So if you have some old tires, you can try to cut it out. But bicycle tire normally is only rubbers and the fabrics threads actually built into net, because the pressure and the force required for the bicycle tire is smaller compared to the cars. Cars, then you will have steel wires and so on in the system. That's why how you distribute these threads and the wire will affect the homogeneous of the material, and then your tires will not be perfectly balanced. So that's why every time you change your tires, you must do balancing. Okay? So rim homogeneous metal with fairly uniform geometries and cross section. So because this one they can make sure it during the design stage. Tire is a composite of the synthetic rubber elastomer and the fabric cord or even metal wire inside there. So it actually compressed in the mold and steam cure at the high temperature. So this result that it will vary in density and the mass distribution, right? So for static balancing, so this is not ideal as it is thick in Excel compared to its diameters. Okay, or someone shared the video of how tires is manufactured, if I'm not mistaken. Okay, so now we talk about this. So static balancing is not sufficient for tires, right? Because its axle compared to its diameter is basically larger, right? So you may have, for example, 16-inch, or we talk about 14-inch because my old Vera has a 14-inch wheel, right? So you have a 14-inch rim. So normally you may put the tires of 185, 60, then they call it R14. Okay, so any of you know how to read the car tires? Since you are mechanical, so I will explain this a bit. Okay, because at least we have to know this. So 185 is actually the width of the tires, right? So 60 is the ratio between the thickness of the tires to the width of the tires. Okay. So then this 14 is the rim size that you can fit in. Okay. So that's why when we say tires have low profile tires, we always look at these numbers. The low profile tires may be at the 40 or even can go down to 30, right? And so on. So you want a wider tire, so you choose a bigger number here, right? But you always have to make sure it fit to the rim. Okay. So this is how how we name the car tire. So if you have a car in your house, so later you can check on this. Okay. So the width, the ratio between the thickness of the tires to the width, and then this is the rim size, right? Not the outer diameters, it's actually the rim size, okay? So if you want to do we want to do the static balancing, so one of the way is to suspend the tires. For example, now we talk about the wheel in a horizontal plane on the cone through its central hole. So what it means here is that now you have your, I draw some cross section of the tires. So this is your tire. The center part there, I draw it in the red color. There is your rims. So you have the center hole, right? So what you can do is you can put the cone and then hang this up onto some structures, right? Then you try to check whether this tires is in level. Okay, you put the level meter. Okay, it's just very cheap, the water level. So you can place this on top. So you see whether they are on the flat horizontal location. For example, if this is low, you put some mesh here to level it. Okay? You just add the mesh onto this side. So this one will come out, this one will go down until it level. Right? So this is how you can do for what we call a static balancing. Okay? So this is how we can do, right? Using the bubble level. Right? So the bubble level meter is always like that. Then there is a cut off at the bottom, and they have a water tube with the bubble in the center, with the bubble. So if this is put on the level, flat horizontal level, so the bubble will stay at the middle, right? If it's tilted, then this bubble will move to left or right, right? Depending on where is the incline direction. So that's why static balancing basically is not that difficult to do, right? It can be done easily because it involves solving the balancing in the static condition. But if we go for dynamic balancing, as mentioned, the car tire is not sufficient if we just do the static balancing. So we'll do the dynamic balancing. So this is a better approach, okay? But the issue here is that we need a dynamic balancing machine to do this balancing work. So this is a schematic diagram of a very old tire wheel balancing machine. Right? Why I say very old is if you look at that, the drive motor is at outside. Right? Nowadays, all the drive motor is keep inside the machine. Okay? So what you have to do, or what actually they do on this system is that you will see that you have a shaft mounted on two bearings, and then this two bearing is fitted with the what we call it the force transducer. So you'll measure the force at this location, and then your wheel will be attached to the shaft here. So the shaft will also need a shaft encoder. So this one is basically to detect the angle of your unbalance, right? Because what happened here is when you measure with this force transducer, every time there is a centrifugal force acted, right? For example, at this direction, so then it will correlate to the where is the location of this force is being applied. So it means that actually then there is an unbalance on the tires, right? But if this tire is totally balanced, then you won't have this oscillating force on this side as well as this side, right? So this is what actually you can see. So that's why the drive motor, so how it actually function is the drive motors will actually contact, you have to push. This is an old type. So you have to push this lever and make contact to the tires. And then this drive motor will start to spin this wheel up to certain speeds, right? So then you will have to detach, right? Detach this drive motor away from the wheel, then only the measurement will start, right? Because you cannot measure with the drive motor attached to this, because this will give a force. So your force transducer always find out, hey, there is a force acting in this direction. Okay? So you must detach and let it rotate freely. So in future, you go to a tire workshop. When they do balancing, you can stand at the side. So you will listen to the sound that initially, then when they press the start button, you will hear that there is an acceleration sound where the motor is actually spinning up the wheel, and then suddenly there will be a sound like the wheel, the drive is detached from the system. Actually, then by that time only the measurement start. Okay. So the figure 12-12 shows schematics of such a device used for balancing wheel and tires or any other rotating assembly. So basically anything you need dynamic balancing, you can put it there. So the assembly to be balanced is mounted temporarily on the axle, or we call it a mandrel, supported bearing with the balancer. So the two bearings are each mounted on the suspension of which content of a transducer or a force transducer that measure the dynamic force. So with the force transducer contain a piezoelectric crystal which deliver a voltage proportional to the force applied. So this is just an explanation of the transducer. So normally they use the piezoelectric sensor as a transducer. So this voltage is amplified electronically and delivered to the circuitry or software, which can compute its peak magnitude and the phase angle of that peaks with respect to the to sometimes reference signals. So the reference signal is supplied by a shaft encoder, as I mentioned, on the mandrel, which provide a short duration electric pulse once per revolution in exactly the same angular location. So this encoder pulse trigger the computer to begin processing the force signal. These are used to trigger the recording of each data sample from the transducer in exactly the same location around the shaft, and provide a measure of shaft velocity of our electronics counters. So this assembly to be balanced is then spun up to some angular velocity, usually friction drive contacting it to its circumference. So as I mentioned, nowadays they don't contact to the tires, they contact to the shaft itself, the rotating shaft. Okay. So the drive torque is then removed. Okay, as I said, you have to remove from the drive, and the drive motor stops. So allowing the assembly to freewheel, okay, free rotation. Then the measuring starts, and the dynamic force of each bearing then can be measured simultaneously, and their waveform is stored. Okay. So the force signal are sent to built-in computers for processing and computations of the needed balance mass and its location. So location normally we refer to is the angle. Okay. As I mentioned, because the wheel, most of the time the only location you can put in the balancing mass is at the outer part of the rim by itself. So the data needed for the measurement are the magnitude of the peak force and the angular location of those peaks with respect to the shaft encoder reference angles. So the axial location of the wheel rim inside and outside edge with respect to the balance machine transducer location are provided to the machine computers by operator measurement. That's why this is what I mentioned. Okay. So the rim inside and outside edge, so it will be keen. Okay. So from this data, the net unbalanced force and net unbalanced moment can be calculated since the distance between the measured bearing force is known. So what it means here is because these two is design. Okay. So that's why this one is known. So they can easily compute the distance. So the mesh radius products needed in the correction plan on each side of the wheel can then be calculated. So the correction radius is always the wheel rim size, or wheel rim radius. And then the balance mass and the angular location are calculated for each correction plan, and then with having the needed mass are clipped onto the inside and outside wheel rims. Okay. So here is still use the word clip, but nowadays if you don't use steel rim, you only stick the balance mass, no more clip. Okay. Okay, so this is how we can do for balancing of this vehicle or automobile wheels. Okay. So the other things, or previously we already mentioned about the linkage. The linkage, if you measure the force at the O2 or in O4, so you also find out that the force is not the summation of force at that point is not zero. The dynamic force is not zero. So that's why we also have to do a balancing of a linkage. Okay, so we have a 4-bar linkage, the 3-bar slider or 4-bar slider linkage. So we also have to do the balancing. Okay? So there are many methods. So for example, complete balance of one dynamic factor, we call it the shaking force, at the expense of other factors such as the shaking moment. So a complete balance of any mechanism can be obtained by creating a second mirror image. Okay. So what it means here is, because now you have one linkage. Okay, so what you can do is, for example, we call it 4-bar sliders. So we have this. So now when this start to turn, okay, and this start to move back and forth, so this point, at this O2 point, you'll get the shaking force. So what you do is, you can put the exact linkage on the mirror side. So you put it here. You put another one, same mass, same linkage. Okay. So when it start to move, it will always be counter. Okay. So if you want to know this is one of the reasons why Subaru is using the opposed engine. And also, how to spell Porsche? Porsche is also doing this. Okay? So in the market, so basically these are the two main car manufacturers who are still stick with this concept. Okay? So they are using the opposed engine, where actually this is one of the main reasons why they keep it. So the engine by itself will be naturally balanced in this way. Okay? So using this mirror image linkage, then it can cancel all the dynamic forces and the moment in the system. Okay? Certain configuration of multi-cylinder internal combustion engine do this, as I mentioned here. You can check the Subaru car. They are very determined to continue using this system. So the piston and the crank of some cylinders cancel the inertial effect of the other. So this approach is expensive and only justified if added mechanism serves some second purpose, such as increasing the power. Else, if you just add a dummy, then this is not economical. So car is fine. So you create another combustion here, another combustion here, so you increase your power. Okay. So most practical linkage balancing scheme seems to minimize one or more of the dynamic effects by redistributing the mass of the existing linkage. These typically involve adding counterweight or changing the shape of the link to relocate their center of gravity. Okay? As with any design endeavor, so they are trade-off. Okay? So eliminating shaking force usually will increase the shaking moment. Okay? What you mentioned here is this one may not be always possible. So that's why if we are not using this, then we can use other things like counterweight or redistributing the mass in order to change its center of gravity. Because the further the center of gravity away from the center of rotation, then the biggest or the highest the unbalanced force. So what we try to do is you try to move the center of gravity to the center of rotation. That is the best. Okay. So for example here, this is a linkage. Okay. This is a 4-bar linkage. So you can see that link 2, you have a center of gravity here. Okay. The center of gravity for CG2, and then CG3 is here, CG4 is here. So at this instant, I always use the word instant because for our mechanics of machine, our thing is keep moving. So the next second, everything will be different. Right? So at this instant, we have the CG2, CG3, CG4 here. So if you calculate the what we call it, the global mass center, so it will be somewhere here. Right? I mean, you combine the CG2, CG3, and CG4. So the central gravity for this linkage will be at this CGT at the distance of RT. Right? So you can see that this will give us the mr omega square. Right? So the centrifugal force. So for this instant, we can actually easily balance it by creating another mass. So I can put another CGT here, RT here at the opposite direction. So at this case, I measure the force here, the dynamic force here, it will be 0. But the problem we are facing now is when the linkage moves another 1 degree or another 2 degrees or more. This center of gravity is keep changing. There is a challenging part of the linkage. So then you cannot put a fixed balance mass here. Okay? So they are the problem we face. Okay. So for this one, actually we can look at the example he gave. We have a figure 12-5 here, showing the 4-bar linkage to which the balance mass have been added. So you can see that the balance mass here. So note the counterweight placed on the link 2 and the link 4 at the calculated location for the complete force balance. So figure 12-6a show a polar plot of the shaking force of the linkage without the balance mass. So the maximum force that we can measure is 2000 Newton at the angle of 15 degrees. But then we have figure 12-6b. It shows the shaking force after the balance mass is added. So the shaking force then is reduced to almost zero. So this is the linkage information, L1, L2, L3, L4. So this is link 1, link 2, link 3, link 4, the link length. And then there is a rotating speed, 50 radian per second. That's why he will get this value. So if you rotate faster, this will be higher. Okay. So he actually run this simulation. This one is through a simulation or through a programming calculation from 0 to 360 degrees. So incremental of the angle is 5 degrees. Right? So he inserted all this. So what it means here is you can see that every line here, every line is 5 degrees apart. So you plotted all this. That is how you get this line, this graph. Okay. So what it means that it is finding F21. Okay. It is finding F21 for every angle of the theta 2. So theta 2 0, theta 2 5 degrees, theta 2 10 degrees. So every angle you calculated. So you find the F12. Then you can plot this. Okay. That's why in the exam or even assignment, I don't ask you to plot this. For example, this one is 5 degrees. So how many times you have to solve? You have to solve 72 times. Okay. The 9 equation. Okay. 72 times of the 9 equation simultaneously. Then only you will get this graph. Right. So this one normally you can put in the program or you can develop the Excel in order to do the calculation. So you can see that the force is keep changing. The F21, it can reach almost 2000. It should be measured this way, 2000, right? 2000 Newton over here at the 15 degrees. Okay. You can see that at a certain point, the force is very small. Right? So what they did is they add on these two counterweight. Okay. So what happened now is you can see you still see the line, but the scale here now is only 0.04 Newton. Okay. So it means that the force has been reduced greatly from 2000 to 0.04. Okay. So this is at 50 radian per second speed. Okay. So you will get this value. Okay. So this is a total system you measure at the link 1. Okay. So now what he did is he break down. Right. It break down into F21 and F41. So what happened here? Just now is the total. We just put a sensor at the ground here, so you'll measure this graph. Okay. So now I put a sensor here and here, so I will get this and this. Okay. So that's why the previous graph, this one is the combination of these two. right? That's why when you add it, you will not reach up to 3,000 over Newton, okay? Because there is a counter force between these two locations. So, but if you look at only the F21, so you basically reach somewhere about 3,400 Newton. Okay? So this will affect your pin size also, your pin size at the F21. So means that your bearing or your shaft that you install here have to withstand the dynamic force of 3,400. Similarly over here as well, right? There is a maximum force that you have to cater, right? But when you put the balancing mass, so relatively you reduce the amount, so you can see that your connection at the O2 and the O4 can also be reduced, right, greatly. So the small residual force seen in the figure 12-6b are due to the computational round-off errors, right? The method gives theoretically exact result. The pin force at the crank and rocker pivots have not disappeared as a result of adding the balancing mass. However, figure 12-7a and b. Hey, where is the it's over here. Shows the force on the crank and the rocker pivot after balancing. These forces are now equal but in the opposite direction. So after balancing, the pattern of the pin of the force at the pivot O2 is the mirror image of the pattern of the O4O. Okay. So what it means? Okay. Then I have to apologize. Basically, even here, you also have a similar two graph, but it didn't plot. But what happened here is the figure 2 point is after the balancing. So what it means here is at this angle, this force will be balanced by this force. So when we calculated the overall force, it will be 0. So this part will be countered by that. Right? So it means that the pin force is still very high after the balancing. Right? So the net shaking force is the vector sum of these two sets of forces for each time step. So the equal and opposite pair of a force acting at the ground pivot at each time step created a time-varying shaking couple that rock the ground plane. This pin force can be larger due to the balance rate, and if so, will increase the shaking couple compared to its former value in the unbalanced linkage. So one trade-off for reducing the shaking force to 0. So this is a trade-off. So the stress in the link and pin may also increase. Right? So just to recap. So this is a force measure at the link 1, right, when it's unbalanced. So this is a force. It can be measured when it's balanced over here, or the link 1. The problem we will face is at the O2 and O4, whether it is balanced or unbalanced, there is still a force, right, over there. Right? So one of the problem we might face when we added this counterbalance mass is that there is a possibility that our pin force is increased. So we call this pin force. Okay, there's a possibility of an increase in the pin force. Right. So there will be the trade-off of the system. Right. So, but normally the ultimate target we want is to reduce the force at the link 1. Right? We want to reduce this because this is what being experienced. Right? For example, you have this system ground mounted onto your floor. Right? So what we don't care on. So normally this one is only designer care on how much force is acted on the O2 and O4, but the user is much more care on how much shaking force is actually exerted to the floor. Okay, if this is lower, then it's better. That's why we will reduce this to this, so that the ground link 1, the force they experience is basically 0. Right? But then the trade-off here is the O2 and O4 will have a larger pin force, right? In most of the case. So that is regarding the force on the link 1, O2, and O4. So there is another balancing issue. It's actually on the top, right? The T12. Individually balancing a link which is in pure rotation by the addition of a counterweight, which have the same effect of the increasing of its mass moment of inertia. So the flywheel effects of the link is increased by this increase in its mass moment of inertia. Thus, the torque needed to accelerate that link will be greater. Okay. So what it means here is, for example, now I have a mass M(R) here. So if I put the mirror M and R here, so my mass moment of inertia will be increased because the torque is I alpha. So when this is increased, my torque will have to increase. So that's why he said we need a higher torque in order to accelerate. This is acceleration, accelerate the linkage. So if we put this in, the input torque will be unaffected by any change in the I of the input crank when it's run at the constant angular velocity. Right? So what it means here that even when we increase this, it will only affect how we accelerate the linkage. But if the linkage is rotating at the constant velocity where the alpha is 0, then the running torque, or we call it we can call it a running torque, will not be affected. Okay? It will only affect the torque required to accelerate the linkage because of this theory or this phenomena. Adding counterweight to a rotating link necessary to force balance the entire linkage both increases the link mass moment of inertia and also unbalance those rotating link in order to gain the global balance. Okay, so this one is just highlight the just now. If you put the balancing mass, right? So what will happen is we will increase the mass moment of inertia. We will also increase the unbalance on the pin, right? On the O2 and O4. But then our global is balanced. The shaking force is balanced. So balancing an entire linkage by these methods then can have the side effect of increasing the variation in the required input torque. We already discussed on this on the flywheel previously, right? On the previous chapter, we talked about flywheels, right? There's why we need the flywheel is because the torque is varying, okay? So the peak and the minimum has a very huge difference. So we need the flywheels to actually levelize the input torque required. So the problem now is when we add in the balancing mass, so this effect the variation of the torque will become much more higher. So this will lead to a larger flywheel is needed to balance the linkage, right? in order to achieve the same coefficient of fluctuation. Okay. So we have this figure 12-8 shows the input torque curve for the unbalanced linkage and for the same linkage after complete force balance has been done. So the peak value of the required input torque has increased as a result of a force balance. So what it means here is before balancing, we will get this curve. So the peak torque is only 137 Newton meter. Okay. After we put in the balancing mesh, these two, then we find out that the torque curve for one cycle will become like that, and the maximum peak at the 174 Newton meter. So actually, even you see that the minimum is much more lower than the initial one. Okay. So this will give the problems where we have to balance the system with to balance the torque or to levelize the torque with the bigger flywheels. So you can see that the average torque after the balancing is higher than the before balancing. So this is a trade-off. However, the degree of increase in the input torque due to the force balancing is dependent upon the choice of the radii at which the balance mass are placed. So the extra mass moment of inertia that the balance mass added to the link is proportional to the square of the radius to the center of gravity, because mass moment of inertia is mk square. So this is the radius of gyration. So that's why he mentioned here is the square of the radius. Okay. So that's why by greatly reduce the radius of gyration of the system of the link, then we will be able to reduce this the variation of the mass moment of inertia. So Weiss and Fandon has shown that a circular counterweight placed tangential to the link pivot center will give a better result on this. So what it means here, even we need m mass radius products, right? So now, in order to reduce this torque effect or the mass moment of inertia effect, we rather choose a smaller r, then we can have a bigger m. Okay. So that's why what he did here is, instead of creating a short link with the mass further away, so now we create a larger mass which is closer to the center of rotation. Okay. Okay, so this is about this one we will still discuss in the engine balancing. So the next one is on the shaking moment. Right? So shaking moment, or we call it MS, is a force balance linkage. In the force balance linkage is the sum of the reaction torque T21 and the shaking couple. But in this case, we try to ignore any external applied loads. So the formulas can be written: the shaking moment is equal to T21 plus R1 multiplied with F41. So what happened here is this is O2, this is O4. So we have a linkage. So we take the moment at O2. So we have T21. And then we have the force. For example, this force now is at this place, F41, and then the radius, R1. All right. So we take the force, multiply with this, plus the T21. So it will give us the moment of this system. So in general linkage, the magnitude of the shaking moment can be reduced but cannot be eliminated by means of mass redistribution within its linkage. Complete balancing of the shaking moment requires an additional supplementary link and or a rotating counterweight. So many techniques have been developed that uses optimization methods to find a linkage mass configuration that will minimize the shaking moment alone, and in combination with minimizing the shaking force and torque. So that's why we always have a problem where we have shaking force, shaking torque, and shaking moment. Improving this, affecting this, and this. You improving this, you may affecting the other two, and so on. So that's why this is you don't have a exact solution. This is always what are the trade-off you will have to make. Okay, we call it trade-off of the system. Okay, which is more crucial for you. Okay, so that's why we have to they have to make a compromise, right, into each other. Okay, so now there is a method here on balancing the shaking moment of the linkage. So one of it is called the Birkhoff method. So this is a simple and adopted, but it only limited to inline linkage, whose link CG lies on their respective link center. Right? Inline means like this. So the center of gravity must be stay on the line center. Same as this one. The center of gravity must be lie on the line center. Right? In addition, a coupler must be reconfigured to become a physical pendulum. Right? This is the one. Such that it is dynamically equivalent to a lump mass model as shown in the 12-10. So this is what we call a pendulum model, and these two has the same, we call it the dynamically equivalent. Mean that either this system or the system here, the dynamic property is the same. Okay, so for example, this is a rectangular bar, the pin is there, so I can model this into two mass M1 and M1 here with the distance of P. Okay, so if you calculated the I, the center of gravity, they are actually same, okay, between these two as well as this. So the coupler shown in figure 12-10 as a uniform rectangular bar of mass M, length and width H. In the figure 12-10B as a dog bone, then the coupler lump mass will be in pure rotation. So three requirements for dynamic equivalent. So remember, there will be three requirements you need. Okay, so I already write two here. The third one is the mass. Okay, so both systems, the upper one, this one and this one, must have same mass, same as this one and this one. They must have same mass and same center of gravity. Okay. CG is the same, so it's over here. So this one is over here. So same center of gravity. And also same mass moment of inertia, I. Okay? So same CG, same I. So this is the three requirement. So the first two requirements here can be easily fulfilled or satisfied by just placing the mass at each pin, right? So if I take the m divided by 2, mean m1 is m over 2. So I put m over 2 here, m over 2 here. You will get the same mass, same center of gravity. Okay. Then the third one, then we have to calculate the radius of gyration, which is k equal to square root of I over m. So this is how we can do the calculation. Taking each lump separately, right, means we have the left and right. Yeah? As if the massless rod will split at the center of gravity into 2 rods each of length L, which of length B, and then we specify the mass moment of inertia is IL, right, at each lump. So we are trying to find that IL, so for each lump mass, the mass moment of inertia is the I over 2. So this is the original I. So we can also write it as a MLB2. So this is the mass radius of gyration, or here is a B, okay, B squared. So try to rearrange it. So that's why my I will be equal to 2mlb squared. So then it will equal to the mb squared, because 2ml is actually b. Okay, this is the first condition we try to fulfill. Okay, so from here then we can find out that the k is, because k is I over m, so I here over m, right? So that's why then we get back the b, right? Or which is a over 2. So where is the a? A is the distance between the two pins. So for the link configuration in figure 12-10A, this will be certified if the link dimension have the following dimensional ratio. So this is slightly complicated because of the extension here, the E. Okay. So the formulas is given E over H is equal to half times square root of 3A over H square minus 1, and then minus A over 2H. Yeah? So this is the formula given. So if you unless you are keen to find out this, then you have to study on this geometry. So from the link configuration in the figure 12-10P, the length E of the added material of with H needed to make it as a physical pendulum. So we have another formula here. So there is given over here A, B, C, D. Okay, so you can also refer to the textbooks. So then we have the second step is to force balance the linkage with this modified coupler and define and required counterweights of the link 2 and link 4. So the shaking moment can be counteracted by adding the adding the gear inertial counterweight to link 2 and 4, as shown in figure 12-11. This must turn in opposite directions to the link. Such an initial counterweight can balance any planar moment that is proportional to an angular acceleration and does not reduce any net initial force. So the shaking moment of an inline 4-bar linkage will be given as this. Okay. Just a second. Okay, so what it means here is how we calculated the shaking moment for the inline 4-bar linkage. Okay, so we can calculate the A2, A3, and A4 for link 2, link 3, and link 4. So because link 1, again, link 1 is ground, so link 1 no effect. Okay, so we only have link 2, link 3, link 4. Okay, so we just, this is the formula is given. Okay, so just now here he mentioned that we can actually counter react the shaking moment with the gear inertial counterweight. So what we do is we put these, okay, which has the flywheel here. We call it the initial counterweight, and then put a gear attached to this link. So the reason here is so that the rotation of this link 2 and the gear is at the opposite direction, same as this. If this one rotate here, this will rotate in the opposite direction. Okay, so this will help to balance in terms of shaking moment. So just now when we talk about these two, this two is actually referring to the coupler. Okay, you go back, you have to restructure again. Previously, when we discussed about this, okay, we discussed about this. We said balancing to the this side and this side. So you can see that we do nothing on the coupler. Okay, so that's why when we come to this part, this is more focused on the coupler. Okay, so that's why at the end we can model the 4-bar linkage in this way. So we have a counterweight for the link 2, and we can have the they call it force balance mass of the link 4, and then we can also balance the thing using the physical pendulum mass of the coupler. Right, so there is all the three things happen here. So based on the formula just now, then we can calculate the shaking moment. Okay, so we have this I from 2 to 4, which is link 2 to link 4. And then shaking moment can be force 0 if the I2 is equal to negative A2, I4 is equal to negative A4, A3 is equal to 0, or we set the K3 square is equal to R3 times A3 minus R3. So there's a A3 here and the R3. Okay. So with all these condition that we described just now, so this will lead to the a set of 5 design equation that must be satisfied. So this is all the 5. Okay, so means that this one will become here, this one will become here. Okay, and then we have the previous one, the MR, M2, R2, and M4, R4. So this is what all the 5 equations that we can apply in order to have this shaking moment balance. Okay. Right? Because what we need this. Okay. We have to calculate what are the flywheel that have to add onto the system. Right? So everyone quiet, because too complicated. Okay. So there are a few things we are trying to do here. The 5 equations will tell us what's supposed to be the I2, what's supposed to be the I4, okay? And then what supposed to be the, you can see, what's supposed to be the mass moment of inertia for the link 3, link 2, and the link 4. So with all this done, then we will be able to balance the shaking moment. Okay. So the rest, the beginning of all of this is just a derivation. So to apply it, actually what you need is the equation we have here. Okay. The 5 equations. Okay. We have here to solve your problems. Okay. So there is balancing topics. Okay. As I mentioned, this part we will still use it in the engine dynamics. Okay. So any questions? You can always ask me even though after the class. Okay. There is a lot of your friends now start asking me questions. Okay. So you can just feel free to ask me. Okay. I will try my best to answer you as soon as possible. Okay. Even during the weekend. So the best, one of the best option is you can get the textbooks, okay, so that you can read the description in a more detailed manner, okay. I think there is more than enough for today, okay, because of this balancing of the linkage part. You need a lot of time to digest. So I think I will stop the meeting now so that you can have your time to digest the slide. Oh, there is one question on often we talk about adding mass for balancing. How about removing mass? So this one, removing mass, we will talk about in the engine dynamics. Actually, for them to balance the crankshaft, they remove mass. Right? That is possible. Right? So it's always based on your design constraint. Right? If your space is allowed, adding mass is the easier one, because removing mass is very challenging. Right? You cannot. When you remove mass, you have to confirm. Right? Where is the location and how much mass you want to remove. But adding mass is a lot easy in practical. You can simply add and take out the mass. Right? But removing mass means you for example, in the crankshaft, they will drill off the material. So once you drill, if you drill too much, then there will be a problem. Okay. For example, that's why removing mass is also depending. Another friend asking if remove mass will destroy the structures. So that's why if you are planned or if you design your component to be able to remove mass in order to do the balancing, so normally that additional material that you put in your in your design is actually not relevant to your structures. And that's why then you can start to remove mess. For example, crankshaft, they purposely add the wedges, the mess in the crank, right? So that it can actually be removed after this. It actually doesn't affect if you don't put that amount of mess there, it actually will not affect the structures, right? The structure is still work as what it's supposed to be without the mess. That's why if you look at the industry, in majority is adding mess instead of removing mess, right? Because you are not trying to make your parts heavy and then only you start to remove the mess slowly, right? So you want to make things as light as possible, as less material as possible. That is what your boss will ask you, right? But for car engine, they actually found the adding mess in the crankshaft actually create a lot of problems because of the geometry change. So that's why they fix the geometry first, then they're removing the material from the geometry, so the overall design will not be affected, right? Just for example, I have a fan. If I want to do balancing of the fan, it's easier for me to add some weight sticker onto the fan instead I go and drill some hole on the fan. So it will affect the fan functionality, right? So any more questions? If not, just make sure you take your attendance and then you can leave the meeting. So thank you very much. So my subject is